70% of the Earth's surface is covered by water. And much of the history of man's discovery of the Earth is linked to oceans. From the fragile boats which sailed along the Mediterranean coasts to the majestic ships which sailed off to the New World, the evolution of seagoing craft and navigation tools has ceaselessly pushed man to break the barriers of the oceans. Frédéric Restagneux is a physicist and CNRS researcher. He's setting off on a journey in the wake of his distant counterparts to find out more about which technology and scientific innovations enabled man to sail farther and farther away, taming the winds, the waves, and even the ice. A scientific investigation to understand how man was able, down the centuries, to build ships, defy storms, and conquer the oceans. Saint-Nazaire, the STX shipyard, which specializes in the building of gigantic cruise ships. Frédéric Restagneux will discover the secrets behind the construction of one of the largest cruise ships in the world. The ship measures 315 meters long, 43 meters wide, with an air draft, the distance between the water and the highest point of the ship, of 65 meters, the equivalent of a 20-story building. It's a genuine floating city which can carry 7,000 passengers.
In terms of size, or can ships get even bigger?
The size limits of ships are based on the ability of ports to receive them, or to the shipyards with infrastructures capable of building them. As for technological limits, they've always existed and we've always managed to go beyond them. So any technological limits that exist today will certainly go beyond them tomorrow.
Stretching the limits, pushing back the boundaries. That's how man, in just a few millennia, has become master of the oceans. A history of seafarers and explorers who, down the centuries, have developed more and more accomplished shipbuilding technology. Frédéric Restagneux heads to Marseille to trace one of the first great...
The boat was built employing the processes that were typically in use in antiquity. But the great originality is that this one was entirely assembled with ligatures, so it's also known as a sewn boat. The construction of a boat like this would have required 5,000 hours of work on the timber and 3,000 hours just to tie the ligatures.
Constructed according to the technology as described by Homer in the Odyssey, his epic tale of Ulysses' sea journeys, this gyptus boat also has the typical propulsion system of antiquity, a square sail, a row of oars, and two lateral rudders, one on either side of the boat.
So it was a fantastic boat for sailing off to conquer the known world at the time.
Not really. This is a regional coastal boat. At 10 meters long, it has a good load capacity. So it was used for fishing, transporting local merchandise, transporting people. It was a kind of neighborhood van. But the Greeks did have other vessels. We know, for example, from the famous historian Herodotus, that Greek colonists also sailed on pentacontours, large ships with 50 oarsmen, which must have been between 25 and 30 meters long. But these were mostly like sewn boats, like this one too.
So it's believed that it was on long boats of sewn-together planks that the Phocaeans explored the whole Mediterranean before founding and colonizing Marseille. A feat that's surely of interest to scientists. Digital tools now give us a better grasp of the techniques used by shipbuilders during antiquity.
When you look more closely at its construction, you see it has all the features of a boat built with wood. There's the central timber beam, the keel, usually in some kind of hardwood. To this are joined the stern post at the back and the stem at the front. This constitutes the backbone of the boat. Onto this backbone, the side planks are attached to form the outside of the hull, and then the transversal reinforcements are also added.
In those days, were all boats sewn boats?
Not all of them. The Phoenicians, for example, used a different technique with tendons and mortices, which would later be adopted by the Greeks and Romans. The principle is to bore holes into which you insert a tongue of wood, called a tendon, which is then fixed with a peg. This holds all the planks tightly together. This technique allowed the Greeks to overcome a number of weaknesses present in sewn boats. It also enabled them to construct bigger vessels with more complex shapes and a longer seagoing life.
Once this empirical know-how had resulted in a more solid hull, this assembly system would enable the construction of huge galleys driven by several rows of oarsmen.
What scientific knowledge had been firmly established by that time?
There were people like Archimedes who had written his treatise on floating bodies, which sets and solves a series of mathematical problems to do with ships' hulls.
In the 3rd century BC, the Greek mathematician and physicist established the founding principles of hydrostatics. In his treatise on floating bodies, he explained that due to gravity, when a boat is on the water, its weight is pulled downwards, but at the same time, water pressure exerts forces across the entire submerged surface hull. He thus determined that an object in water is buoyed up by a single force equal to the weight of the fluid displaced by the said object. This is called Archimedes' principle. For a boat to float, its weight and the upthrust must be equal. If too much weight is added to a boat, it will be heavier than the amount of water displaced by the hull. The upthrust therefore becomes insufficient to counter the weight of the boat, and the boat sinks. So to increase buoyancy and thus sinking when taking on heavy loads, you simply have to increase the volume of the boat. Throughout antiquity, the known world stopped with the Mediterranean. The ocean was feared and believed to be uncrossable. At the time, the absence of charts and compasses obliged most seafarers to play it safe by sailing close to the coasts, hopping from port to port. Then, as maritime transport began to grow, elders created signaling systems which made the sea less dangerous. Frédéric Restagneux catches a plane to Ushant. Located 20 kilometers off Finistère, this island is one of the westernmost in France. Known as the Century of France, it's surrounded by 5 lighthouses to guide sailors along a coast with a long history of wrecks. To understand the importance of the role lighthouses played in the rise of sea travel, Frédéric Restagneux visits the heritage-listed Créache Lighthouse on a rocky spur on the northwestern point of the island. Erected in 1863, this century-in stone is equipped with one of the most powerful beams in the world.
How long have lighthouses actually existed?
Since antiquity, we naturally think of the Lighthouse of Alexandria, one of the 7 wonders of the ancient world, which was erected on an islet called Pharos, thus the words phare, pharaoh, etc. in South European languages. It was built in the 3rd century BC and was destroyed by an earthquake in the 14th century.
What were the steps between the lighthouses of antiquity to the one at Ushant, which is very modern?
There were several steps. Firstly, Pharos was simply an open-air wood-fired brazier. Next came coke braziers, then oil lamps, and finally electricity, with the invention of the Fresnel lens.
In 1821, Augustin Fresnel, a French physicist and engineer at the Lighthouse Commission, suggested replacing metal reflectors with a glass lens with sections. This lens, soon called the Fresnel lens, is composed of a central convex disc and concentric rings which act as a prism. On exiting the lens, the beams of light deviated by the concentric rings find themselves parallel to each other and pointing in the same direction. So the process prevented light from spreading and was so successful that the Fresnel gradually began to equip lighthouses all over the world.
With a lens like this, the beam must reach really far.
32 nautical miles. That's almost 60 kilometers. The most powerful beam in Europe.
Throughout antiquity, notably thanks to lighthouses, seafaring developed in the Mediterranean. But not only there. Driven by their desire to conquer the oceans, several people embarked on great expeditions, such as the Vikings. In the 8th century, a fleet of longships sowed fear in the West. After Western Europe, these unparalleled navigators explored the North Atlantic, colonizing Iceland and Greenland. In April 2016, the Draken Harald Haarfagr reproduced the incredible voyage which had taken the Vikings to America in around 1000, 5 centuries before Christopher Columbus. From Norway, the modern-day Vikings crossed the North Atlantic following the same routes their ancestors did a millennium ago. At the end of an eventful crossing lasting almost 6 months, they reached their final destination, the United States. While today it's largely recognized that this people of navigators succeeded in completing one of the greatest maritime conquests in history, their feat remained unknown until the 19th century. In Western Europe during the Middle Ages, the scientific precision of new navigational tools was added to the expertise of seafarers. The compass and the astrolabe, the forerunner of the sextant, were on board every boat and ship. In the 13th century, Europeans began to have a new image of the world, thanks to portolan charts born out of the expansion of trade and drawn on a compass rose canvas. From then on, all the tools were in place to enable the great explorers, like Vasco da Gama and Christopher Columbus, to embark on the conquest of the oceans. But before setting off on long expeditions in search of the New World, ships needed to be totally redesigned. Frédéric Restaño heads to Mazagon in southwestern Spain. It was on this coast on the Atlantic that most of the great exploration ships were constructed. Majestic carracks and caravels, like the now Victoria, which was part of Magellan's fleet and the first ship to circumnavigate the world. The man who built the replica continues to sail this legendary ship.
5 ships went on Magellan's expedition, and this one was the only one to return, captained by Magellan's second-in-command, Juan Sebastian Elcano. 246 men left, and only 18 came back.
The now Victoria was far removed from the ships of antiquity. The oars had disappeared, giving way to 4 masts and almost 300 square meters of sail, indispensable for the propulsion of this imposing merchant ship.
How did you work out how the ship had been constructed?
At the time, for this kind of ship, there were no blueprints. So for 3 years, we dug around in archives, libraries, and museums. And we found 16th century books which explained in detail the techniques used, how they constructed, how they assembled the wooden parts, and how they cut the wooden parts. It was all perfectly explained. The moment they wanted to increase the size of the ships, they needed to be more rigid. They needed to resist bigger waves and a much bigger swell. And that would have been impossible without the strong framework. So the first thing they built was the framework here and the keel here. Once the skeleton was completed, they started attaching the outside planks of the hull from top to bottom with iron nails. Then they added this part, called the crosspiece. And with this assembly, the framework was very rigid.
The invention of the solidly fixed stern post helm revolutionized shipbuilding. The size of the rudder, the submerged part of the helm, could then be adapted to the size of the ship.
You're steering the ship, but you don't have a wheel.
No, they used a tiller before the wheel. It was a revolutionary invention because the helmsman was down in the hold, so he had direct access to the rudder. But this bar is linked directly to the central tiller in the hold, which then moves the rudder. When you're steering and you want to move to starboard, you pull the bar towards starboard.
And you've been around the world with that?
Sure.
Incredible.
Not really. Today we have electronics and weather reports. Elcano and Magellan didn't have all that.
In 1519, in Seville, Magellan's fleet set sail to discover the western route to the Moluccas Islands, the islands of spices, now part of modern-day Indonesia. The expedition crossed the Atlantic to Brazil, sailed along the coast of America, and finally discovered a passage to the Pacific Ocean, the famous Strait of Magellan. Magellan was killed in the Philippines, so it was Juan Sebastian Elcano who completed the first ever circumnavigation of the globe. After almost 3 years at sea, his return to Seville brought formal proof that the Earth was indeed round. The era of great discoveries paved the way for a new period, that of the Great Rush for Wealth. Nations crisscrossed the globe, opening up new trade routes and fighting each other in order to rule the seas. The Renaissance saw the birth of the galleon, then the frigate, warships with several rows of cannon. But the race for naval superiority and the gradual increase in the size of ships was accompanied by a growing number of wrecks. Vessels often suffered from a lack of stability due to an uneven distribution of their loads. The most striking example was the sinking of the Vasa in 1668. At at the time the most powerfully armed ship ever to set sail and commissioned by the King of Sweden himself. It foundered with the first gust of wind barely out of the port of Stockholm. So in the late 17th century, it became a matter of urgency to work on the stability of ships. French mathematician and physicist Pierre Bouguer published the solution in his Traité du Navire, the first real treatise on naval architecture. This work delivered the indispensable complement to Archimedes' principle for the scientific calculation of a ship's stability. When a ship takes on water, it rolls and then lists due to the waves or the wind in its sails. When the ship lists, the change in the volume of water moving inside the hull creates a variation of the center in Archimedes' principle. Knowledge of the position of the center of upthrust and progress in mathematics allowed Pierre Bouguer to precisely calculate the position of the meta-center, which in turn permits a naval architect to predict a ship's stability. If too much weight is placed high up on a ship and the center of gravity passes above the meta-center, the ship becomes unstable and keels over. However, if the center of gravity of the vessel is situated below the meta-center, the ship can return to its original stable position. In the 19th century, more and more cargo ships crisscrossed the oceans with very precisely calculated loads. That was the case of the historical sailing ship, the Belém.
The Belém was launched 120 years ago in Nantes. She's a cargo sailing ship which brought back sugar, cocoa, and rum from Brazil and the Caribbean. To compensate for the lack of merchandise when sailing empty from Nantes, she took on ballast. This ballast was granite, which was offloaded in Montevideo. And in fact, parts of Montevideo were built with granite from the Belém.
How many kilos of ballast did a ship like this need?
She's currently holding 400 kilos for her 800 metric tons. It's a small percentage of the ship's weight, but well placed in the bottom of the hull and gives it a lot of stability.
Although the Belém used to take on 675 metric tons of merchandise, today one of the last witnesses of the golden age of sail is a sailing school. It takes an average of 1 hour to hoist the total 1,200 square meters of sail.
What differentiated this ship from earlier cargo ships is that the sails are fragmented in several places.
The Belém has 21 sails, so you can break up the set and determine which sails you hoist, or not.
She has 3 masts, but also a metal hull.
Yes, people are surprised to find out that the Belém has a metal hull. Remember that construction in steel was at a height in 1896, and metal hulls have a big advantage over wooden hulls in many areas. For example, the ship is more solid, because while steel might fissure, it won't break apart like wood. There's also a larger length-width ratio with a metal hull, which means ships can be longer and thus much faster. This ship was at the transitional stage, and when steam was developed, most of the great sailing ships, part of our maritime heritage, were taken out of service after World War I.
The Belém has a maximum speed of 12 knots, that's 22 kilometers per hour. In the early 20th century, it took her a month to cross the Atlantic. Steam divided this time in two. Tank, which used scale models pulled through a long stretch of water to test resistance on the careen. The laws of hydrodynamics present similarities, so it's possible to extrapolate measurements made on scale models and apply them to life-sized ships. The models, at a scale of 1 to 20, subjected to propulsion tests, but also to extreme condition resistance tests. Thanks to careen testing tanks, engineers were able to design more and more high-performance ships capable of crashing through the highest waves. But man still had one more battle on his hands before he could master all the seas on our planet, the conquest of the poles. After the first scientific expeditions of Peary and Amundsen, the Arctic and Antarctic oceans became much coveted. For trade, year-round routes were opened through the frozen oceans. Frédéric Restagnaux flies off to Kemi in Finnish Lapland, close to the Arctic Circle. This small port town lies to the far north of the Baltic Sea on the Gulf of Bothnia. The waters of this 725-kilometre-long strip of sea are icebound for half the year. This is where the Sampo is moored, an imposing 75-metre-long icebreaker. In service since the 1960s, this ship was once a tug which rescued ships trapped by the ice. Today it crisscrosses the frozen sea for polar cruises.
Our hull is much thicker than normal cargo vessels. Normal cargo vessels, they have, let's say, between 10 to 20 millimeters thickness of the plates, and we have a 32, so it's much more. And also those bulkheads, normally they have between 60 centimeters. We have a double, I mean those ribs on the hull, so we have a double.
Other than its reinforced hull, the Sampo is fitted with a powerful engine which propels it through frozen waters. But how do you deploy enough power to drive this steel monster of 3,500 metric tons?
We have like 4 main engines. Each produce like 2,000 horsepower. It means that main engine produce like 8,000 horsepower total. Normal cargo ship has 4,000. It's like half.
On icebreakers, a particular propulsion system predominates, electrodiesel. The Sampo's huge diesel engines produce electricity through 4 generators. It's this electricity which drives the propellers.
This kind of propulsion give very fast maneuvering to forward and backwards. He and ship will be stuck on the ice. He might turn this direction back and try again.
How does an icebreaker actually break the ice that's in its way?
So this Sampo is 3 times heavier than the same size of the cargo vessels. We have to get more mass to go through into the ice. And if we are comparing icebreakers for the cargo vessels, the hull of the icebreakers, they are round like an egg. We don't have a keel at all. So it's much easier to climb up above the ice. And then ice blocks going under the bottom, and then propellers push it away.
I guess there must be situations where you find yourself totally blocked by the ice. What happens then?
It's very, very dangerous situation if the normal cargo vessel will stuck, and if there's a strong pressure, for example, due to the wind, it can be crashed whole the hull of the vessel. Like I'm crashing the tin can, for example. So it's getting crushed, and then it will start leaking, and then there is a risk of going down. The most important thing for the icebreakers is assist the cargo vessels. If they are stuck, so icebreaker will cut it out from the ice field and then make fast with the towing line and start towing merchant vessels to the easier ice situation.
What's the maximum thickness an icebreaker can break?
In Sampo, this vessel have been designed for 1 meter 20 centimeters, and it's maximum in situation in Baltic. But it can be also, it's called polar glass, so it's several meters what they can break, so it's much more.
For over a century, science has been helping man to access the most extreme zones. But human activity has also led to global warming, a source of concern for the scientific community, which measures the amount of ice melting each year. The mythic Northwest and Northeast passages, in which so many explorers' ships fell foul, are gradually opening up their doors and creating new corridors linking the North Atlantic and the North Pacific, which are drawing nations in the hunt for new maritime routes. And leading their way, icebreakers have never been performing so well. Near Helsinki, scientist Frederic Restagno visits a Finnish research centre where 60% of the world's icebreakers are designed. Here, scale models are tested in one of the largest frozen tanks in the world. Today, the engineers are putting a 5-metre-long scale model to the test. That's equivalent to a 100-metre-long icebreaker. As for the fine 14-millimetre thick ice, in real life it will be 1 metre thick. The aim of the experiment is to measure the forces exerted on the propellers.
The ship's sailing in the wrong direction as it breaks the ice.
This is actually a double-acting icebreaker, which means that in open water and in light ice conditions, the vessel can go bow first, but in hard ice conditions, it goes the stern first. And the benefit for that is that it's difficult to design very good bow for open water and ice breaking at the same time. So in this case, the bow is designed for open water and the stern is designed for ice breaking.
A concept made possible by a new generation of propeller. To improve the propulsion of ships through ice, the engineers have worked on their maneuverability.
That's one benefit of azimuthing thrusters. They are very good in maneuverings and turning.
Turning propellers which allow icebreakers to reverse in a matter of seconds. Traditionally, ships are driven forward by propellers, which by pushing the water away from the stern makes it move forward. The power supplied by the engine travels along the shaft of the propellers. But to steer the ship, you also need a rudder. In the second half of the 20th century, the azimuth thruster was invented. This enabled propellers to pivot 360 degrees. With this adjustability, this single unit system replaced the propeller rudder dual unit and enabled ships to make faster and more precise maneuvers. In the 1990s, the Pod, the latest generation of azimuth thrusters, saw the day. a Finnish invention which was firstly fitted on imposing icebreakers.
We are building units for world's largest cruise ships, large icebreakers, huge LNG carriers. Well, these units here are about 20 megawatts and weigh about 170 tons. The biggest revolution and the difference with the mechanical thrusters is that we put the electric motor inside the pod, outside the vessel's hull.
What's the interest of fitting an electric motor inside the pod itself?
The Azipod propulsion system, where the propeller is directly facing the water flow. The water flow to the propeller is even, which creates much benefits for the system.
What are the savings in energy consumption?
It varies quite a lot depending on a vessel type. For example, in a typical cruise ship, the gain can be something like 5%. Then you have additional benefits from the general arrangement inside the vessel. As the motor is located on the out part of the vessel, you have more freedom in arranging different equipment inside the vessel's hull. For example, in a cruise ship for passenger cabins or in a cargo ship, you can free space for the cargo, so you get more payload.
Extra space and savings in energy have become major stakes in a sector which assures 90% of world trade. Almost 90,000 ships sail the world's seas, every year transporting over 10 billion tons of freight. And the race for gigantic growth reached a peak with container ships and cruise ships measuring several hundred meters long. Which challenges did engineers have to rise to in order to construct these real-life sea monsters? Back to Saint-Nazaire and the bowels of our giant cruise ship. Over 2,500 people work every day on this giant floating city, with a surface area of 180,000 square meters.
This is the heart of the ship, the main promenade deck where passengers can stroll during the cruise.
Looks pretty long.
It's between 90 and 100 meters long.
When you see a room like this, which is like a huge hollow in the middle of the ship, you don't get the idea of a rigid vessel.
There's a lack of material that guarantees rigidity, so we do a lot of calculations and find lots of tricks to hide the structural elements, which are nonetheless there, like the pillars you see here. Plus there are partition walls closing off these empty areas.
What ensures the ship's rigidity?
Ships are constructed of steel, so it's this material that ensures the ship's rigidity, and the whole ensemble makes the deck more rigid.
But the most complex structural challenge facing naval architects is how to fit the largest number of cabins on a cruise ship. Rooms with large windows and balconies with a sea view, which considerably weaken the ship's rigidity. To meet the demands of the passengers, while also reinforcing the structure of the ship, the engineers fitted crossbeams at each deck. Between each of these steel reinforcements are the cruise ship's 2,246 cabins.
Our cabins arrive prefabricated and we finish them off on board. The most important constraint is width. That's the dimension we agreed upon with the customer. As strange as it may seem, this width fixes the distance between each of the ship's crossbeams.
The engineers are permanently adapting to the demands of the owners, including delivery in record time. On this cruise ship, about a year was required to build and assemble the 80 blocks, weighing in at 70,000 metric tons. In just a few millennia, man has progressed from fragile wooden boats to genuine floating cities. at the same time mastering the planet's entire surface water. But another vast universe still remains to be mastered. The underwater world, a whole new territory to be dreamed of, explored and conquered. For centuries, the depths have inspired storytellers. The most visionary amongst them was Jules Verne, with his tales of Captain Nemo in 20,000 Leagues Under the Sea. In the novel, his heroes explore the ocean depths in diving suits, a technology which in the 19th century was still in its infancy.
Before Cousteau and Gagnon's Aqualung, the sea was a 360 million square meter mirror. So it's only been a very short time since we were truly able to explore and get to know marine life. Christopher Columbus brought America to the Western world, and there were already Native Americans there. Little America. Jacques Cousteau brought us 3/4 of our planet. 360 million square surface meters have become an entire volume filled with extraordinary creatures. That's what Cousteau bequeathed us.
In diving, pressure is generally expressed in bars. On the surface, air pressure is 1 bar, which corresponds to about a kilogram pressing against a surface of 1 square centimetre. As a diver descends, pressure increases by about 1 bar every 10 metres. So the lungs compress. To prevent from being crushed, the air breathed must counterbalance this compression. In 1943, Commander Jacques Cousteau and Émile Gagnon invented the Aqualung, with a regulator which reduces pressurized breathing gas contained in a cylinder to ambient breathing gas which is supplied to the diver. But it was a submarine which allowed man to go even deeper. In 1960, Jacques Piccard and Don Walsh accomplished the feat of diving into the Mariana Trench at a depth of almost 11,000 meters.
1,100 bars of pressure. That's simply colossal. They had no idea whether they come back alive. That was much harder than reaching the moon, and it's still harder than reaching the moon.
Beyond the feat itself, that historic dive proved the existence of life in the abysses, and it launched an era of scientific exploration of the depths. Research centres across the globe, such as IFREMER, the French Research Institute for Exploitation of the Sea, began to develop tools to carry out their missions. On board oceanographic ships, the researchers sent down subs and then robots, like this ROV, a remotely operated underwater vehicle.
This vehicle can descend to 2,800 meters, and it really isn't bulky at all. So it can access spaces which are very difficult to access, the inside of a wreck, inside a canyon, in very fragile places too. So we can get very close up to these structures.
This innovative tool, ORIS 3D, uses very high-definition underwater photogrammetry processing, which allows researchers to study the depths with precision. Wrecks, archaeological remains. Plus it can also map inaccessible undersea caves. The team sends the ROV down into the Cassideña Canyon in the Calanque National Park, a protected natural area. The aim of the mission, to study changes in the coral massif.
The ROV's at the bottom.
What depth is that?
Just over 200 meters, 205 meters, pretty deep.
20 bars?
20, yes, already beyond conventional diving.
Is that the result of what we saw earlier?
Yes, this is the massive of white coral we saw earlier and which have been 3D modeled. We can move the objects we're studying around. That allows us, as you can see, to travel inside the 3 dimensions of this living complex. Because all of this was built by living beings. Look at the detail we get when we zoom in. You can see each individual, which is only a few millimeters in diameter. So being able to archive all this in 3D might enable us to come back in the future and to reanalyze what we have identified and to see if it has grown, if it has died, or if other species have moved in. So we'll gradually find out more about the distribution of the biodiversity, notably in deep environments.
The ocean depths, beyond 200 meters, account for about 66% of the surface of the planet. For a long time inaccessible, they're now within man's reach. And it was in 1977 that they gave up their greatest mystery. On the oceanic ridge of the Galapagos Islands, on the border between 2 tectonic plates, American geologists partnered by French scientists from Ifremer discovered for the first time hydrothermal sources. Hot water coming from the bowels of the Earth. In this hostile environment, on these undersea volcanoes, the astounded researchers discovered a profusion of life. In Brest, at Ifremer HQ, a new technology is allowing researchers to study particular ecosystems, the Subsea Observatory. Thanks to a cable network of 800 kilometers resting on 2,000 meters of seabed, linked up to cameras, researchers can connect live to a hydrothermal source off the coast of Canada.
We'll plug it in, and there we are. It looks a bit strange, because we're in waters at about 400 degrees Celsius when they come out. The pH is very acidic. There are all kinds of heavy metals, cadmium, arsenic, lead. We're at a depth of about 2,200 meters with a pressure of about 200 bars, the equivalent of a cow standing on your fingernail. What's more, there's a lot of natural radioactivity. So at first glance, you'd say life is impossible. But amazingly, there are extremely rich oases of life present.
What's the temperature there?
Not too high, just under 20 degrees where the fauna exists. Then there are the big black smokers, which spew out fluids of several hundred degrees Celsius. What happens is the very hot fluids come into contact with very cold seawater, and that leads to the precipitation of the chemical elements contained in the fluids. And it's this precipitation which gradually forms the large mounds of sulfur, for example, which the fauna feeds on.
So close to home, a totally unknown world. You're the new explorers.
New explorers, but of our own planet. That's what's so astounding. We barely know 5 to 10% of it. What remains to be explored is vast.
Will man one day have a perfect knowledge of this mysterious world which has for centuries attracted and enthralled explorers and scientists?
We know nothing about the subsea world. There are countless things to discover, describe, and understand. We're diving into a mind-spinning infinity. Mind-spinning.
We have to see what there is under the sea. Human genius and its technology is giving us the possibility of exploring this new field that's opening up to mankind. Tomorrow's pharmacology will come in some part from the sea. Our future food will come in large part from the sea. We need to realize what this universe represents. It's the one remaining territory for the evolution of mankind.